All right, first off, a warning or kind of a confession. I put function in quotes because this isn't actually the way we define a function in mathematics. Normally, in order to define a function, we have to actually specify the domain and the range. Now, they don't need to be the same thing. We could send a function from one thing to another thing, or we could send a function back to itself. But in any event, in order to define a function properly, we need to define the domain and the range of where that function goes from to. This task isn't meant so much as a lesson, but more as an example of a mathematical exploration. So encourage students to try grappling with what it would mean to extend a function from one place that they understand to a bigger place. And so there are a couple of possibilities here. Firstly, we could keep track of remainders. So we could divide our function from the integers and remainders to the integers and remainders. And note, the idea of sending the function from integers plus remainders to integers plus remainders would make a lot of sense in the real world if we were dealing with something like sharing ping pong balls among students. You know, ping pong balls being a thing that you can't just rip apart or they're no use anymore, right? So in this instance, 3 would go to 1 plus remainder 1. But if we did that, this might suffer from a problem of what would it mean to apply our function twice? So 7 would go to 3 remainder 1, and 3 remainder 1 might go to 1 remainder 2. But 1 remainder 2, well, that's probably better. If we've got those 2 remainder, we could just divide those up. So actually 3 remainder 1 might make more sense to send it to 2. The problem is that the 1 remainder 2 only sort of makes sense because we could always divide that 2 up already. Another way to attack this might be to include any denominator that is a power of 2. So this might make sense in the real world if we had, say, a bar of chocolate that we were trying to divide up. Because you can take a square of chocolate and divide it in half. So now if I have 3 pieces of chocolate that I want to divide among 2 people, well, each gets 1.5 pieces. This adding in all of the possible denominators that are powers of 2 turns out to be really well defined. And it kind of makes a lot of sense. And it avoids adding in all of the possible fractions, which of course is another possibility. We could actually just extend this to the function on the rationals or the fractions, right? Because you can always break something up into a fraction. Dividing by 2 makes sense. Now, what does this have to do with the rest of the sequence that we've been looking at? Well, it's kind of interesting to think that if we only kept track of the remainder, we didn't worry about the rest, we just kept track of what was left over, then dividing by 2 sort of makes sense modulo any other prime. For instance, modulo 5, dividing by 2 is the same as multiplying by 3. It's kind of crazy, huh? I'll say that again. For instance, modulo 5, dividing by 2 is the same as multiplying by 3. And why is that? Because multiplying by 3 and then by 2 is the same as multiplying by 6, which is the same as multiplying by 1, mod 5. And conversely, multiplying by 2 and then by 3 is the same as multiplying by 2 times 3, which is 6, which is the same as multiplying by 1 as well. That is, either way, multiplication by 2 sort of undoes multiplication by 3, or multiplication by 3 sort of undoes multiplication by 2. Weird, huh? Certainly something fun to leave students thinking about. Anyway, thanks for joining us for the finite forest sequence. Glad you could stay with us for the whole journey. Hope you've actually now completed the entire spotted exploration. And we look forward to seeing you back on a new exploration soon. Infinity is just around the corner.